Welcome to Unit 4 of Calculus on Vectors. We're going to be talking about optimization and just general applications of derivatives in this unit. It starts off with this note on velocity and acceleration. Some of this will be a review from advanced functions. Some of it you may already know from physics. If not, then we'll cover everything that you need here. So some definitions: the velocity of an object is the rate of change of its position. So if there's a function that represents an object's position at any given time, then if you were to analyze the rate of change of that, you would find the object's velocity. If you analyze the rate of change of velocity itself, you get acceleration. So it's kind of like you have the position function, which is s of t, then your velocity would be s prime, and your acceleration would be s double prime. Basically just continuing to analyze the rate of change of each function. A quick note that the word speed is not actually the exact same thing as velocity. They both refer to a rate of change, but speed is kind of like the speedometer on your car. It doesn't pay attention to what way you're going, so you can't ever travel with a negative speed. I'm traveling 50 kilometers an hour, whether it's east or whether it's west. So velocity can be negative. Speed can't be. Speed can only be, as the lowest it can be is 0. So that's why you see speed here is equal to the absolute value of velocity. It's just always a positive number. First thing to understand here is the idea that when an object is speeding up, that means that the acceleration and the velocity are in the same direction. So either a times v, they're both negative, and therefore when they multiply you get a positive, or they're both positive. So this would be an object, let's say, moving to the right and speeding up to the right, accelerating to the right. If the object is slowing down, then your two signs, your first derivative and second derivative, are competing with each other. So you have one's positive and one's negative. So imagine you are moving to the right, but you are accelerating to the left. This would be, pressing your brakes in the car, for example, where you're traveling in one direction, but your brakes are pushing you, slowing you down in that direction by accelerating you in the opposite direction. And so that's what you're seeing here when something slows down. So again, if you have your note from Unit 3 where we talked about concave up increasing, right? Concave up increasing would be speeding up. Concave down decreasing would be speeding up. And then a mixture of the two would be slowing down. So like concave up but decreasing, or concave down but increasing. Those would all be, that's another good way of looking at this, kind of looking at the four different shapes. If v is positive, the object is traveling to the right, or a positive direction. If vt is less than 0, it's, let's say, in a negative direction. Just to specify. If v of t is at 0, then the object's momentarily stopped. It could be at a maximum or a min, depending on what we're looking at. Okay, let's try this one. So it says a ball is thrown directly upward with an initial velocity of 24.5, then its height after t seconds is given by this equation. When does it reach a maximum height? What is the height? When does it hit the ground? So on and so on. Of course, you don't need any calculus to solve this, but let's do it the calculus way just so we can kind of practice. So if you have 24.5 t minus 4.9 t squared, right? This is our object's been thrown up with an initial speed of 24.5, and it accelerates due to gravity. Of course, comes back down to the earth. And so let's just have a quick look at what we see here. So it's asking us a couple of things here. It says, when does the ball reach its maximum height? Of course, from working with parabolas, there's different ways you can do this, but let's do it the calculus way. So again, we're going to rename this one S. So that's the position function. If we take the derivative of s, we get s prime, which is the velocity function. Now the velocity function, again, it's worth noting, it starts at a high positive value and is constantly going down until 0, and then constantly going down until a negative value where it's hitting the ground here with a speed of, let's say 35 or so. Or sorry, that's not hitting the ground. It's hitting the ground here with its 24.5 meters per second. So the point here is that the same thing we've been observing all course is that if you look at the root of the derivative and then you notice that the derivative changes signs from positive to negative, we know that that pattern is familiar to us. It's a maximum. It's increasing, 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 stops, and then decreasing, and therefore we can find our moment of where it's at its highest point. So s prime of t equals 0 would be one way of solving this one. So for example, s prime of t equals 0, and we find that that's true when s prime is at 2.5. So we'll just write that down. So sorry, when t equals 2.5. That gives us a velocity function in s prime of 0. What is the maximum height? Of course, would be what is s of 2.5 itself. You actually plug it in and find out, so we'll just quickly do that. S of 2.5 returns 30.63, so again, just plot that point up there, right? And that, that's where we find the max, so 30.63. When does it hit the ground? So it hits the ground when s of t itself is 0. So you have to take that function and factor it. We just quickly factor it. If we take out the negative 4.9 to the front, and then we get t squared minus 5t, and so we get, which is equal to negative 4.9 t minus 5 and just a t. Okay, so you can see it hits the ground at 5 seconds, so let's say t equals 5. With what velocity does it hit the ground? So that we want to know. We want to know what's s prime of 5, because we're basically plugging in 5 into the velocity function. Let's find that one. So s prime 5 is negative 24.5. We'll just quickly graph that, 5b, and see that it is on the velocity graph at the moment when the object hits the ground, right? So this moment here, it hits the ground at 5 seconds, and then you can see the speed at this time is negative 24.5, which is the same speed that it was launched with because of the way that this works. Okay, so I'm going to say negative 24.5, and the negative just means it's pointed downward. Find the acceleration at 2 seconds. Okay, well, fortunately for us, if you take the derivative of s prime, you get the acceleration function, which is just a constant. That makes sense because the only force acting on this object is the force of gravity, and it acts with it causes an acceleration of negative 9.8 meters per second squared, so we get 9.8 there is the answer. So s double prime of t equals negative 9.8. So therefore, s double prime of 2 is also equal to negative 9.8 because it's equal to that all the time. So again, a quick sketch of them would look something like this. We just get rid of this, let's get rid of the vertical line here. So the position function is in green, the velocity function is in red, the acceleration function is in blue. Okay, and this is just describing the motion of a ball being thrown up in the air and returning to Earth. Now, when you're talking about an object moving in a horizontal way as opposed to moving up and down, so the one we just looked at was something being thrown straight up into the air and then returning back down. This one, we're talking about an object moving left to right, or right to left. So if v is a positive number, the object's moving in a positive direction. If v is a negative number, it's moving left. I don't really know why it's saying this. We don't really know if it's moving right or left of its initial position unless we know where that is. So let's just ignore that for a second. If v is positive, it's moving to the right. If v is negative, it's moving to the left. If v is 0, you're momentarily stopped. Okay? So maybe you're changing direction, or maybe you're like a car that just stopped at a stoplight and are about to speed up in the same direction you're already going, right? And that would just be a horizontal tangent, an increasing horizontal tangent as opposed to a turning point. Now, the object can also be said to be moving towards or away from the origin if the combination of signs of position and velocity are positive or negative. Again, just imagine this, and you'll find this is actually a pretty easy thing to do. Imagine you have a line here. Actually, let me do this here. It would make more sense. Imagine we have an object here. Okay, so let's just make it this point. And we'll say the origin is here, this point B. So just rename this to the origin. Now, if you imagine that A is moving to the right, okay, so let's say A is moving to the right. Okay, like it would be here in that picture. Now, think about this for a second. The position of A is positive. A is on the positive side of O. The velocity is positive. So if you have an object that is already to the right of O and moving to the right, it is going to move away from the origin, right? Now contrast that with, what if A is on the left, right, and the velocity is still pointing to the right? Then you would say it's moving towards the origin, right? So what all this is trying to say is it's a very precise mathematical way of saying it, but just imagine that if the object's position and velocity have the same sign, the object is moving away, because S times V is positive. We know that happens if S and V have the same sign. And if it has the same sign, it's one of two cases. You're already to the right, and you're moving further to the right, or you're already to the left, and you're moving further to the left. Now, on the other hand, if the object's position and velocity have different signs, then you're moving towards the origin, right? And again, just imagine, let's go back to our diagram quickly for a second. Moving to the right, but standing to the left means I'm getting closer to the origin, right? So I'm moving towards. Okay, what we can do here is we can look at an example and just try. I think like going through this example will really help sort of solidify some of these concepts. So it says the position of an object moving on a line is given by such and such function, and then we got to do a couple things with it. So 2t cubed minus 21t squared plus 60t. So let's do this. So 2t cubed, or x cubed, minus 21x squared plus 60x. Okay, so we got something like this. Okay, so you can see the object is going to kind of rapidly move away, and then turn around and come back for a little bit, and then turn around and move away again. And if you want to watch this object, we can just kind of watch it for a sec here. If we, let's say we had a point A, and then a time t. And let's say A is defined by the time and then the f of t. Sorry, that's not what I want to do. F of t and 0. So it's going to be moving in a horizontal line, right? So here's A. And you can see it kind of like, even within half a second, right, it's gone. Because it's already moved all the way over there. It's moving really fast at the beginning, right? Let's zoom out a bit. You can kind of get a better sense of what this thing's doing. So here's what the object's doing. It moves to the right. And then you can see it slows down, slows down, slows down. And then it turns around. And then it turns around again. And then it goes off. Okay? Let's just watch that one more time just so we can observe. Okay, this time I'm going to track another point that's on the function itself. Okay, so let's make another point B. We're going to define it as t and f of t. Okay, now watch how B moves as A moves. Remember, A is the object. It's moving in a horizontal line. B is simply a point on the function. and I'll pick this up on the next section.